Good evening, everyone. So today we have the first lecture in our series on listening from the budding technocrats. And this webinar series is organized by the computer chapter of IEEE Kolkata section. So we have with us Jishnu Mukhoti, and he is an alumnus of our Computer Science and Engineering Department of Jadavpur University. So he will give a lecture on simple, fast, and practical uncertainty estimation in deep learning. So I now request Dr. Chandri Chaudhuri to introduce Jishnu, and over to Chandri.
Thank you, Dr. Basu. It is my privilege and to introduce Jishnu. He has been a student of our department, and we always, are very much inclined to listen to our alumni members of the department. So it is really a great moment for all of us. So, just to introduce him, Jishnu is a second year PhD student at the University of Oxford. His supervisors are Professor Philip Torr and Professor Yarin Well. He was a student of BE in Computer Science and Engineering at Jadavpur University from 2012 to 2016. Being the topper of his batch, he received the prestigious gold medal at Jadavpur University. He was also awarded the Best Project Award by Tata Consultancy Services for his B final year project. He obtained the MSc degree in Computer Science from University of Oxford. He is interested in simple ways of quantifying uncertainty from deep neural networks. His notable contributions are his work on calibrating deep neural networks using focal loss and deterministic neural networks with inductive biases capture epistemic and aleatoric uncertainty. So let us all hear from Jishnu. So Jishnu, yeah, the stage is yours.
Thank you so much. Thank you so very much for inviting me to give this lecture. And yeah, so I've been doing my PhD and I'm in my second year, and I did my bachelor's there. So it's an amazing honor for me. I can start sharing my screen. If that's okay for the slides.
Okay, so you start sharing. Let me see.
Okay, can you see my screen?
Yes.
Yes.
Perfect. All right.
So before you start, just I'm adding one point that to all the viewers, because there is a live stream going on. So to all the viewers who have questions, any queries, you can just type your queries in the YouTube live stream chat box, and at the end of the session, I'll try to present that to Jishnu, and we can have an interactive chat session. So it will not be a audio interaction, but you can, if you type your questions in the chat box, so we can directly post it or send it to Jishnu for you to answer. So thank you. So we are over to Jishnu.
Okay. Cool. So today I wanted to talk about simple, fast, and practical uncertainty estimation in deep learning. And this is very much what I have been doing during the course of my PhD. And even I kind of started off from when I was a master's student here in Oxford. So first of all, what do we mean by uncertainty? How I would like to say in like a very gist is basically to know what you do not know. So for instance, in deep learning, you have classification algorithms, and if you want to train a classifier that kind of identifies dogs and cats, say, then what do? You you take a data set with labeled images of dogs and cats, and then you push it into a deep neural network, and you train the network using normal training procedures. And once your network is all trained, then it should generalize to previously unseen images of dogs and cats. And it should be able to identify, oh, this is a dog or this is a cat. Great. However, what if it suddenly sees a picture of a raccoon, which it never has seen before? What should it do then? Ideally, it should say, well, I do not know. I've never seen this picture before. But do deep neural networks do that? And if not, how do we fix this? So this is basically knowing what you do not know. And this is basically very important for uncertainty quantification. And why should we care about this? Because deep learning is now being applied in many applications because of its success, because of the high accuracy that deep neural networks are achieving on curated data sets. So we are applying it everywhere. We are applying it to autonomous vehicles, we're applying it to medical diagnosis, and these are very safety critical applications. So it is utterly important for models to, in addition to be able to quantify their, in addition to be accurate, it should be very good at quantifying its uncertainty as well. So now, how do we get uncertainty? So before we move on to the question of how to measure uncertainty, let's look at our inputs. And just now we saw this example of a raccoon, which the network has never seen before. And if we pass the image of a raccoon to, say, a deep neural network trained on cats and dogs, then it should ideally say that I've never seen this before, right? If it's able to quantify its uncertainty properly. However, we can also have another kind of input, which is, say, a very noisy or blurred out image of a dog. However, it is very much an in distribution image because the network has been trained on images of dogs. In this case, it should kind of say that, okay, I don't know what this is. This looks noisy. Why I gave these two examples is because on both these examples, the network can actually misclassify. Because one, the network has never seen before. It's a class which the network has not been trained on. The other one is a blurred out kind of noisy image of something that was in distribution for the network. However, the network can still misclassify, and anything that the network is misclassifying or making incorrect predictions on, it should ideally say, I don't know. However, why these two examples are important is because how we deal with these two examples. Now, if we get a raccoon and if the network says, I've never seen this before, how do we fix it? If we want the network to start identifying raccoons, then we have to retrain or maybe fine-tune the network on labeled raccoon images. However, if this is just a noisy example, then we just need to clean it up and we provide a cleaner version of the same image, and the network should identify the dog just fine. And it's because of this difference in our attitude to fixing the network or to dealing with that example that we need to distinguish between these two kinds of responses from the network. And that is why we need these two kinds of responses from the network in the first place. Now, these two kinds of responses actually deal with different kinds of uncertainties. And these two are, one is epistemic uncertainty or model uncertainty, and one is aleatoric uncertainty. So epistemic uncertainty, so yeah, I really liked this. I found this on a blog, and I've referred the blog here. And I really like this because it provides a really good visualization of what epistemic uncertainty and aleatoric uncertainty is. So when you have data, you imagine that in your deep learning setup, your training data is coming from a data distribution, right? You have a data distribution and your training data is basically sampled from that distribution. So of course, anything that you have not seen in your data distribution or anything that you have not seen in your training data is technically out of distribution. So it's an infinite set, like your out of distribution can be anything, right? However, even in distribution, even among the data that you have seen, there can be noise. Why? Because of exactly like the example that we saw before. You can have imprecise observations taken from your measuring device, say. So that the uncertainty induced in the model because of such imprecise measurements is called aleatoric uncertainty. And the uncertainty in the model because of lack of knowledge is epistemic uncertainty. So we now can see how where exactly our aleatoric uncertainty would lie and where exactly our epistemic uncertainty would lie. Our epistemic uncertainty would lie in places which we have never seen before, or in case of data which we have very few samples of. So we really do not know what we need more data to kind of reduce our epistemic uncertainty. Aleatoric uncertainty is because of observation noise or ambiguity. So aleatoric uncertainty is kind of irreducible unless you get better instruments to make your measurements. And I actually made, so this one shows aleatoric uncertainty really well, but it does not really show epistemic uncertainty. And epistemic uncertainty has another name, as I said, it's model uncertainty. And it kind of quantifies, why it's called model uncertainty is because the model should ideally be not confident. Like there could be several models that could fit a region with high epistemic uncertainty. And to see that, I made this little visualization as well. This is a simple regression problem, just like before. It's a polynomial regression, and you have certain data points, and you can see that there are two regions where you have a set of data points, and then there are certain regions where you do not have any data points. And that's good, because if you actually fit multiple models, then you would see that there is a huge disagreement between these different fit models in regions where you do not have any data. So essentially, your model disagreement could be a measure of epistemic uncertainty. And you would see that your models are disagreeing a lot on areas where you have no data, which is why I kind of like labeled these out as high epistemic uncertainty and regions of low epistemic uncertainty. And regions of low epistemic uncertainty can or may or may not have high aleatoric uncertainty. But aleatoric uncertainty does not make much of a sense for out of distribution regions. So hopefully, now that we are kind of clear on epistemic and aleatoric uncertainty, we want to see how we get these values from a neural network and what would be like the easiest ways of getting these. So before we go on to like methods of getting these, I wanted to kind of talk about this philosophies of probabilities. One is frequentist and one is Bayesian, right? That's most important like philosophies. And frequentist is where you always measure a probability based on repeating experiments of an event. So you have multiple experiments, and you see how many times your event that you're checking the probability for occurs in those sets of experiments. And that's how you quantify. And that's why it's basically the frequency or the number of times the event occurred in your total number of experiments. And that is how you measure frequentist probability. However, for Bayesian, what you have is that you have an initial belief that an event will occur, okay, right? Like if you're talking about a Bayesian probability of an event, you initially have some belief, which kind of quantifies your prior knowledge about that event occurring or not. And then based on observed data, you kind of update your belief. So right now, I kind of believe, so I included an XKCD joke here as well, which I found really funny, but I'm not going to explain that much. What I would like to say, like what is particularly different about Bayesian probability is that you can actually quantify some kind of probability for events that you have never seen before. So for instance, if the sun suddenly exploded, that is something that is a very, very rare event. So what is the probability that the sun will explode? And since you do not have experimental data, you cannot make like 1,000 suns explode. You do not have much of a data as to quantify the probability of the sun exploding. So you need to have some kind of initial belief on what is the probability of the sun exploding. And provided that eventually, in 10,000 years, we have enough data to see how many suns exploded, not 10,000, probably way more, but then probably we can make an updated belief on such events. In short, like you can talk about Bayesian probability for events that you have never seen before. So we can actually apply both of these methodologies in quantifying uncertainty for neural networks. So let's first try frequentist, right? And now, like most or all of examples that, like, because I have worked mostly on multi-class classification, so I will be talking about multi-class classification. But of course, the same philosophies can also be extended to regression. And although I have not found a lot of work on that, but it's still quite an active research area. And of course, the philosophies can be extended to regression as well. So let's get back to our previous example of cute dogs and cats. And let's increase one class, and let's say that we have trained a network on, say, 3 classes: dog, cat, and horse, right? And normally, and since I'm talking about multi-class classification, you end up with your network produces a softmax distribution, right? Which is basically a categorical distribution where your categories are your classes. So you have 3 categories here: dog, cat, and horse. And your network produces a vector which is normalized over this 3 categories and sums up to 1, right? So obviously the network has been trained on dog, cat, and horse, and it recognizes the dog really well, and it produces a value of 0.7 for the dog. And this 0.7 is actually can be considered, of course, because this all sums up to 1, since it's a categorical distribution, 0.7 is a probability, right? And this probability, now the thing is whether you want to consider this probability as a measure of your confidence. And it seems really simple to do that, right? It seems really easy and simple to do that. So let's try that. Let's say our probability from this softmax distribution is actually our confidence. Now, if it is so, then it should be calibrated. And what do I mean by calibration? So let's say that we have a data set. And of course, we are making some predictions over the data set, and this is the test set. So this is basically from the we are assuming from the same data distribution that we have been trained on. And let's say this is the set of examples. And among these, like, we have predicted or classified certain, like, say, the first 3 rows of these images with a probability of 0.7. And say the next remaining rows with a probability of 0.8. Then a calibrated classifier, 70% of the first set of images will be accurate, and 80% of the second set of images will be accurate. So what I mean is, if you are predicting with a certain probability estimate, then for all the samples that you have predicted with that probability estimate, and by probability estimate here, I mean the maximum of your softmax distribution, for all the samples which are predicted with that probability estimate, if that probability estimate is P, then P% of that samples should be, or a fraction of P of that samples should be accurately predicted. And this should hold for all probability estimates between 0 and 1. And that is where you are completely calibrated. So that is kind of like the mathematical definition. If you are predicting with a probability of P, certain Y, like an output of Y, then the actual likelihood of that sample being that particular class or being correctly predicted should also be P. And this should hold for all possible probability values. Now, how do we measure calibration in deep neural networks? Of course, like the interval 0 to 1 is uncountably infinite. So you have to kind of find an approximation. And the most well-known approximation is something called the expected calibration error, and also something like a visual representation of it can be found in reliability plots. And I'm going to describe both here. So what you do, you want to have all the probability estimates between 0 and 1 calibrated. So of course you can't do that because it's infinite. So what you do is you make bins between 0 and 1, and you have certain bins. And what you do is for each bin, you see the samples which are lying in that bin, as in which have been predicted with a confidence interval lying in that bin. So for instance, over here, between 0 and 0.1 and 0.1 and 0.2 and so on and so forth, you bin those samples in those particular bins. And now you compute the accuracy of that bin just for those samples lying in that bin. And then basically what you want, ideally for a perfectly calibrated model, your bin confidence should be your bin accuracy, right? So you can simply find the absolute difference between the accuracy of your bin and the confidence of your bin, right? And you can make a weighted average of that over all your bins. And that would give you an estimate of your calibration error, which is your expected calibration error. Of course, there can be multiple other ways of measuring calibration error, and there can be other ways of binning. So there are many, many variants of ECE. However, ECE is the most popular, which is why I'm describing it here. And the other thing is that there are reliability plots. So reliability plots is just a visual way of kind of explaining calibration here. So for instance, in this paper, this is like a really popular paper on calibration, which is why I posted it here. And you can actually see what, like, reliability plots give us an additional information in addition to your expected calibration error. Your expected calibration error is actually the absolute difference, but you can be calibrated in two ways. You can be overconfident miscalibrated, you can be underconfident miscalibrated. And it turns out that most neural networks, most current big convolutional neural networks like ResNet, like wide ResNet, and so on and so forth, are actually always overconfident miscalibrated. What I mean by that is, let's look at this experiment. People trained, these researchers, they trained on C400, and they trained two models, LeNet and ResNet. Of course, LeNet is a very small model. Turns out that it's like in the first row, they're plotting for each like confidence bin, how many samples are there in each bin. And in the second row, they're plotting this calibration plot, which is the reliability plot, which is basically accuracy versus confidence. And turns out that, of course, ResNet is much more accurate than a LeNet. And it turns out that it puts most of its samples in the most confident bin. However, it's much less calibrated as compared to a LeNet. So, of course, calibration and accuracy are not always correlated, not always. So your network could be much less accurate, but much more calibrated. But you ideally want something that, is very calibrated and accurate at the same time. So, of course, like as I said, big convolutional neural networks are not that calibrated. And why does this happen, right? So this is from my previous paper on calibration of neural networks using focal loss. In this one, what we did was we started off looking at causes of miscalibration, and then kind of we took cues from previous papers, including this paper, and we did like an analysis on this, and then we figured out like what could be a possible alternative to make calibrated neural nets. Now, it turns out, okay, so what we did is we took a ResNet 50 network, we trained it on CFAR10, and we were plotting we trained it for 350 epochs, and we were plotting the NLL, which is your cross entropy loss, and the entropy of the predicted, like the softmax distribution. And the entropy of the softmax distribution kind of quantifies how spread out the distribution is. So a high entropy distribution would be very spread out, and the highest entropy distribution would be uniform. The lowest would be like, just one class having a probability mass of 1. So as it turns out, and we did this for like both train and test set. So after a certain training epoch, we saw that the loss, which we are optimizing for on the train set, of course keeps on reducing, and it reduces eventually to 0. However, on the test set, the loss starts increasing. And so this is a very well-known phenomenon in machine learning, and it's called overfitting. So it turns out that although the classification error does not really rise that much, on the test set even, the NLL starts rising on the test set. And what does this mean? What exactly is NLL? NLL is basically minus log of the probability with which you're predicting the ground truth correct class, right? So, of course, after a certain point, you have a certain generalization gap, which is you kind of misclassify or make incorrect predictions on certain set of test samples, right? And if you keep on training, as it turns out, you start getting more and more confident on your misclassifications. And which is why the NLL starts rising on the test set, because it starts rising exactly for the incorrect samples. For the correct samples, it keeps on reducing because it's kind of gaining more probability mass on the correct class. However, for the incorrect sample, it starts increasing. And that's what causes this overfitting effect. And why this happens is kind of related to weights of a neural network. Essentially, we want a neural network that's very accurate. However, we kind of train on a proxy for accuracy, which is your negative log likelihood. So even when the network is getting 100% training accuracy, even then, so you can see the train classification error is kind of very close to zero from epoch 150 to 250 and exactly zero from epoch 250 to 350. Even then, you can further reduce your NLL. And when you try to reduce your NLL, you try to get exactly a distribution which is like a probability mass of 1 on just one class. And you do that. To do that, you want to increase or maximize the magnitudes of your logics. And to do that, you want to maximize the magnitudes. You try to increase the magnitudes of your weights. And as a result of which, the misclassifications that you make on your test set also get more confident. And that's how miscalibration is caused, essentially. So now let's talk about how to calibrate a DNN, right? You can do that. The most popular method, there are several methods, and I will leave the interested to kind of explore papers on this. But one of the most popular, or the most popular post hoc method of calibration is temperature scaling. It's a very simple method. What it does is you train a neural network, right? It's miscalibrated. And what you want to do is kind of map those miscalibrated probabilities into calibrated probabilities. And how you do that is by kind of scaling your logits using a temperature parameter. So you could take your logits, you have a single scalar, which is your temperature, and you fine-tune that temperature on a validation set, on a held-out validation set. And once that temperature is fine-tuned, you kind of end up having much more calibrated probabilities at the end. And by more calibrated, I mean lower ECE scores. So this is basically from the paper that I first showed you on calibration, and they showed that among all the post-hoc calibration methods, temperature scaling really does really well. And it has really caught on because of its simplicity. However, temperature, so for like, optimal temperature also can give you a hint as to how calibrated your model is. So if your optimal temperature is much higher than 1, then you know that your model is much more confident, as in overconfident, miscalibrated. So turns out that most neural networks, as stated before, like they are overconfident and their optimal temperature is much higher than 1. However, when you apply that optimal temperature on your logits, it works on both correctly classified and incorrectly classified samples, right? So that makes it underconfident even on correctly classified samples, because your temperature is acting for all samples and you do not know which sample to actually apply it on. So you apply it on all samples. So your temperature scaling makes a network underconfident in general, both for correctly classified and incorrectly classified samples. And also, as seen in a recent paper on calibration, I've referred that here, temperature scaling does not work against when you have like a test set, which is slightly shifted from your training set. Of course, with the same classes, but still slightly shifted from your training set, as in you put in noise or you put in some kind of like Gaussian blur or something like that. Temperature scaling does not really work well in those cases. So can we do better? And turns out that, if we go back here, then we are seeing that, okay, so training on NLL or negative log likelihood or your cross entropy loss has this problem, right? So what if we want to train a network that is more calibrated instead of going for like post hoc calibration? Again, there has been a lot of work done on this, but so my previous work was basically along this line of kind of trying to train a more calibrated model. And you can do it by, so we tried this alternative loss function, and why we tried it, I'll explain why we tried it. It's called focal loss. So your cross entropy loss is basically minus log of PT, where PT is the probability, this is for a single sample. If you put in a sample, your cross entropy loss is minus log of PT, where PT is the probability mass assigned to the ground truth correct class. Focal loss, what it does is it puts in an additional weight on that log PT, and that's 1 minus PT to the gamma, where gamma is a hyperparameter. Now, the intuition behind focal loss is that if the network is actually very confident on a certain sample, then we need to put less weight of the gradients on that sample and more weight of the gradients on samples where the network is not putting that much probability mass on the ground truth correct class. So that's why this particular 1 minus PT. And gamma obviously controls how much this regularization sort of happens. And what was interesting about this loss is that you can actually see that cross-entropy loss is actually an upper bound on the KL divergence, or the Kullback-Leibler divergence, which in very simple terms is kind of like distance between two probability distributions. So if you take the Kullback-Leibler divergence between your actual ground truth, which is your one-hot encoding, and your probability distribution that you get from your predicted, like the predicted probability distribution, which is the softmax distribution, then cross-entropy will be minimized when that Kullback-Leibler divergence is minimized. However, focal loss is actually a regularized, it's an upper bound on a regularized version of that Kullback-Leibler divergence, where the regularizer turns out to be the entropy of the predicted distribution, and the regularization coefficient is gamma itself. So what it does is actually it's also trying to minimize the Kullback-Leibler divergence between the predicted the predicted distribution and the one-hot encoding. However, at the same time, it's also trying to maximize the entropy of the predicted distribution. So it does not do exactly this, because this is another loss function called the maxent loss. However, it is an upper bound on it, right? And so this was particularly interesting, and also the intuition that we want to put less probability mass on samples where the network is really doing well. And so we repeated the same experiment, the ResNet 50 CFAR 10 experiment using focal loss with gamma values 1, 2, and 3, and we found that this NLL overfitting phenomenon is significantly reduced. Like if you look at 3, it is practically not there. Now, why is focal loss doing better? We found that if you take the gradients, if you take I'm not going to go into much detail here, but if you take the gradients of focal loss, and if you find the ratio of the gradients of focal loss with the gradient of cross entropy, then you'll find that focal loss actually starts regularizing the gradients, which in turn starts regularizing the weights of the network. And as I mentioned before, the network is kind of getting miscalibrated in the first place because it's trying to increase the magnitudes of its weights. So what we did as an experiment was to kind of take the L2 norm of the last linear layer and take the feature norm of the previous layers. So we found that if you take the L2 norm of the last linear layer for all these losses, then you find that from the point where miscalibration is starting off, there is a complete reversal between focal loss and cross entropy. In fact, even between the different versions of focal loss, like gamma values of focal loss, there was a complete order change. And so comparatively, weights of models trained on focal loss have lower norm than weights of models trained on cross entropy. And that kind of makes sense because it in terms of like training more calibrated models. So this was great, and we obviously did a large-scale experiment on CFAR 100 and CFAR 10, tiny ImageNet, different data sets, and we found that like overall focal loss variants really worked really well. And we made some variants of focal loss as well in the paper, which I'm not going to go into like greater detail, but feel free to ask me any questions on it. The immediate question was like, what's the gain over temperature scaling? Because we are just kind of measuring on ECE or variants of ECE, right? So even if I apply temperature scaling on a cross entropy model, it's great. The first thing is that, okay, even in terms of ECE, pre and post temperature scaling, the focal loss models perform better. The one great thing about that was that the optimal temperature that we found for focal loss was very close to 1. Which meant that even temperature scaling did not make much of a difference to these models. So whereas the optimal temperature for cross-entropy models was much higher and was like, and this is like applied on the logits, so it makes like a much greater difference on the softmax probabilities just because of the nature of softmax. Which means now the optimal temperature close to 1 means that your model is actually not getting as underconfident as you think on its correctly predicted samples. Apart from this, we also found, so I have not included that slide here, but we also found that on distribution shifted, like when we take like out of distribution data or distribution shifted data, then focal loss actually performs much better, even both pre and post temperature scaling, and temperature scaling, as mentioned before, does not really help in that case. Cool, so this is calibration. This is one of which I think is like the frequentest way of defining uncertainty, and it's very simple. So it's quite attractive in that way that you can just get a softmax probability vector from your model, and you can define an uncertainty estimate on it, and you can calibrate it, right? That's great. Is that all? And as we saw before, we had an example of a raccoon, which the network had never seen before. And this is a class which the network has never been trained on before, right? Can you even define ECE for such out-of-distribution data? You can define ECE when you have some measure of accuracy, because you need to compute accuracy for each bin. What if, like, for a sample where you do not even know what class you have never seen that class before? There is no concept of accuracy there. You just need to say that I do not know, but you can't even define ECE. So how do you even measure performance for a model when such a sample is given, right? So we need something else, of course. And that's how we come to Bayesian. And as I mentioned before, Bayesian is really good for cases where we have events which we have never seen before. What's good about Bayesian is that, okay, like we just said what's good about Bayesian, but what's the main philosophy of Bayesian models is that we have, say, model parameters theta, and we try to model a distribution over those parameters theta, and we initially have a prior, which kind of models our initial belief about what those weights of the model or parameters of the model should look like, and then we train. And while we train, we do Bayesian optimization of those parameters. And while doing Bayesian optimization, we kind of converge the posterior belief on the weights. And so if we converge the posterior belief, so yeah, like impose a prior distribution over model parameters, update your belief by training your data on Bayes' theorem to get your posterior, and sample from the posterior distribution to find your epistemic uncertainty, which is great because ideally, in cases of data which your model has never seen before, your posterior should have very high variance, and you should ideally be able to quantify that and say that I don't know. So that works really well. However, turns out Bayesian optimization is kind of intractable for deep neural networks, so it has not really caught on that well. Exact Bayesian inference and Bayesian optimization. So still, the raccoon is sad. However, we have ways to counter that. That's basically approximate Bayesian inference. And I'm going to talk about two particular papers which are really popular in this field. One is MC dropout. So dropout, as you know, is kind of a very well-known layer initially introduced for regularization mostly, but then this paper found that you can actually use it to do something called variational inference. In variational inference, in very simple terms, you do not want to actually get, you literally cannot get the exact posterior over your model parameters. So what you want to do is you want to get an approximate posterior over your model parameters. And you want to make that approximate posterior as close as possible to your exact posterior. And that is how variational inference works. It turns out, and this paper kind of connects the two dots there, that just training a network on dropout actually performs variational inference on a model. So it's very simple, and that's why it caught on initially. Again, like simplicity really catches on in deep learning literature. I've seen that. So what you do is you train with dropout layers, and during test time, you keep your dropout layers in train mode. So kind of the amount of noise that they're kind of putting into the network remains during test time as well. And for each input, you compute multiple forward passes, and that is actually equivalent to sampling from a distribution, from a posterior distribution, or from an approximate posterior distribution. And of course, the mean of those outputs can be the prediction, and a measure of variance between those outputs can be your uncertainty. So this is great. I mean, feel free to, so I know that I did not really explain why dropout is variational inference, and there is some math behind that, but feel free to drop me questions if you want to get more details on this, or even better, read the paper. The other really, if not the current state of the art, one of the current state of the art is deep ensembles. Again, a very, very simple method, right? So this just says that no need to do anything. You just train an ensemble of networks on the same training set, and that's it. that's pretty much it. You average the predictions of the softmax distributions of all the ensembles, and you take the, say, the entropy of that average softmax distribution, and that's your uncertainty. And why I kind of, so this, it's kind of a controversial thing to say that this is Bayesian, because what is your prior? Immediately the question will come like, what is your prior and how are you actually doing Bayesian optimization here? So I do not call it completely Bayesian, but this is a way of performing Bayesian model averaging. And there has been some work that also says that this is kind of Bayesian model averaging or equivalent to Bayesian model averaging. And I personally feel that it is, because after the training, you can see each component of your ensemble as a sample from a distribution over model parameters. So, and even dropout can be seen as an ensemble where each forward pass is kind of passing through a different network technically, because your dropout layers is connecting different neurons together for each forward pass. So this is Bayesian model averaging. And now let's look at the uncertainty estimates, right? So so I have a deep ensemble here, and M1 to Mn are the component networks of the deep ensemble. All of them get the same input, and they all produce individual softmax distributions, right? What I want to take the entropy of the averaged out softmax distribution, and I'm calling it, let's say, predictive entropy. This can be my uncertainty estimate, of course. There is also something else that I can do. As mentioned before, as we saw before, disagreement between models, or disagreement between models actually captures model uncertainty or epistemic uncertainty. So what we could do, instead of just computing predictive entropy, is we could compute the entropy of all the individual softmax distributions for each component, right? Each of them is producing an individual softmax distribution. You compute the entropy of that, and then you average out the entropy of all the components. So you could compute the entropy of the expected softmax distribution, and also the other way around, you could compute the expectation of the entropies of the individual softmaxes. So turns out that the predictive entropy, which is the first term here, like the upper term here, is actually like mutual information plus the expectation of the entropies, which is the second term here. And predictive entropy captures both aleatoric and epistemic uncertainty, whereas mutual information, which is the predictive entropy minus this second term, the aleatoric bit, captures just epistemic, because this captures just the disagreement between models. So epistemic, so let me give you an example. I'm sorry I did not put it on the slide. It's a really nice example. So if you could have, say, for three classes like dog, cat, and horse, you could have a softmax distribution coming like 0.3, 0.33, like 0.33, 0.33, 0.33, which is like a uniform distribution, right? So that's high entropy. At the same time, you could also have 0.33 coming from all of your individual components. So all of them are like perfectly uniform distributions coming from each individual component of your ensemble, and they're all very uncertain about that particular sample. That's great. So the predictive entropy is obviously the average of all this. So it gets 0.33, 0.33, 0.33, and the entropy is the entropy of whatever that is. Like it's the maximum possible entropy. At the same time, you could also have something along the lines of 1, 0, 0, 0, 1, 0, and 0, 0, 1, where each individual network is very confident on its prediction, but the three networks are completely different, making completely different predictions. So that actually quantifies as disagreement between these different models. And that is what captures epistemic uncertainty, as we saw before. Like the disagreement captures epistemic uncertainty. And the great thing about this is principled in the sense, well, okay, not fully principled, but it follows the Bayesian paradigm. And so, of course, this can work as for MC dropout as well, and for any Bayesian method where you're kind of doing some kind of sampling from an approximated posterior. And I wanted to show you guys this like toy experiment, which shows that why epistemic uncertainty is captured by this term mutual information, and predictive uncertainty captures both epistemic and aleatoric. So this is just a toy experiment where, so the leftmost figure shows the data. And in that data, like, I'm training 5 different models. So it's like an ensemble of 5 different networks having the same architecture. And those were like really small, I think, MLPs. And then I'm actually putting like the softmax probability estimate for the regions of the data and also in between. So you can see that there is data which is labeled, this is a binary classification, and there is data which is labeled 0 between -6 and -4, and then from -4 to -2 it's 1. And there is no data between -2 and 2, and again from 2 to 4 there is 0, 4 to 6 it's 1. Turns out that if I take the softmax entropy, it's very high for the region where there is a transition between 2 classes. So between -4, at -4 and at 4, it peaks. And between -2 to 2, where there is no data, the models are in complete disagreement. Like, it can be, the different models are producing peaks at different areas of that region, right? So this was interesting. And this disagreement gets captured in the mutual information. So you can see that the mutual information is high only in the region where there is no data. However, the predictive entropy captures both aleatoric uncertainty and epistemic uncertainty and peaks at all those regions. And of course, like, there is high aleatoric uncertainty at the transition. So this is great. However, both MC dropout and ensembles are really very expensive, are really very computationally expensive, especially when you're running large-scale real-time applications, right? And to the extent that they are often rendered infeasible. And one of the examples is like semantic segmentation, which I had previously worked on. So I'll show you some results on that towards the end. So what we want now is something that actually can capture both epistemic and aleatoric uncertainty in a single forward pass deterministic neural network. So that's like the end goal, right? And that would really help because you get the speed of a deterministic neural network and you get both epistemic and aleatoric uncertainty, and life's good. So, of course, till now, I have kind of defined epistemic uncertainty as disagreement between models, right? And for that, you need multiple models to have something to disagree on, or you need to multiple samples, and those samples need to disagree, right? However, what if we defined epistemic uncertainty as something different? And this brings me to kind of this entire field of distance-based or density-based models, where you can actually define epistemic uncertainty as something of like anything in my data distribution, anything that is very far away from my data distribution should have high epistemic uncertainty, because it is from I can make the assumption that it is coming from a different distribution where the support of my data distribution or my training distribution does not lie. So of course, we can also define epistemic uncertainty. And this over here, we're again shifting from the Bayesian paradigm. This is not Bayesian. But we can define epistemic uncertainty as like distance or density in some space, or maybe in the data space, maybe in some other space. Like anything that is far away from the data is out of distribution and should have high epistemic uncertainty. So there has been some work on deterministic uncertainty as well. And so these papers, Duck actually came, so both Duck and SNGP, I think SNGP came out in last NeurIPS as well. Duck came out in last ICML. And there is this other paper, which is slightly older, which is Mahal and Abyss. And I will kind of describe all these approaches separately. Okay, cool. So for Duck and SNGP, what you have is you have a feature extractor, right? You have ResNet, you have a feature extractor. And then at the very end of that feature extractor, you get feature vectors, say, right before your last linear layer. There is a last linear layer which kind of takes your feature vector and maps it to the logit space. And the logit space is a vector which is basically it's the same number of dimensions as the number of your classes. So if I remove that last linear layer, and if I take just the features before that, there's like for ResNet, I think they're 512 dimensional. So after that, you remove that last linear layer, and then you put in like a distance aware layer, which can be several things, which can be a radial basis function, which can be a Gaussian process, different things. And And then you kind of train on this loss end to end. And those losses have to be tuned for radial basis function networks or Gaussian processes, something like that. That's great. However, it won't work. Why? Because, as it turns out, feature extractors are really good at making bad features. So they are only trained on in-distribution data, right? And of course, for each in-distribution data, you have a feature extractor, and that kind of has a representation of that data point in its feature space, right? However, as it turns out, they suffer from feature collapse, which is they also map out of distribution data to very in distribution regions in the feature space, which is like overlapping. And this is called feature collapse. And actually, I should have included a visualization, which can be found in, I think, Duck. The paper Duck actually introduces the term feature collapse in the first place. So because there is feature collapse, the distance aware layer won't find any distance between out of distribution points and in distribution points, which makes that's why the whole thing won't work. So what you need to take some extra additional steps, and you need to make a better feature extractor. So what you want to do is you want to kind of preserve the distances that are there in the data space or in the input space, right? So you want to do that by kind of changing the Lipschitzness of your feature extractor. And I'll explain, like, for people who do not know what Lipschitzness is. It's basically the Lipschitz continuity of a function kind of determines how much the value of that function can change with change in your input. So if you constrain that for a feature extractor, then in the feature space, you're constraining how much distance there should be or should not be for distances in the input space. So there isn't a very theoretically sound way of doing it, but there are multiple ways of kind of approximately controlling the Lipschitzness of these large feature extractors. And by feature extractor over here, I mean a large network like a ResNet. So there are multiple ways of doing it. You could actually use gradient penalty. You could use spectral normalization. Oh, I did not include the references for those. I should. I will do that. I'll change the slides accordingly. But there are multiple ways of doing it. So what spectral normalization does is it kind of upper bounds the Lipschitzness. So you cannot actually make it too distant for the same amount of distance in the input space. And for feature extractors like ResNets, wide ResNets, dense nets, which have this thing called the residual connection, which is basically like you have blocks of residual of layers stacked on top of each other, and then you add a residual connection from the beginning to the end, and you add both of those, and then you make your forward pass. So it turns out that if you have a residual connection or a skip connection, then you automatically are kind of lower bounding your Lipschitzness at 1. So your network will have a Lipschitzness, or each such module will have a minimum Lipschitzness of 1. And then you can upper bound your Lipschitzness using the spectral normalization, which you can fine tune. So if your network is bi-Lipschitz, then this does not happen. This feature collapsing does not happen. So you have some semblance of distance in your feature space as well. And then you can apply your distance aware layer and loss and everything, and then this works much better. So these both Duck and SNGP work on these principles, but with different components. So, but the difficult thing with the Duck and SNGP is that you have to kind of introduce this architectural changes with distance aware layers at the end, and then changing feature extractors, and that kind of has a lot of hyperparameters to fine tune, and your entire training process gets affected. So in what comes up next, I'll kind of show how you can get by without doing these things. And one final work that I wanted to discuss is Mahalanobis distance, which is slightly older than Duck and SNGP. And what they do is they do not constrain their feature extractor, but they build a density model on the features, and then they take the density as a measure of uncertainty, or to quantify for OOD detection and stuff. Again, this as mentioned before, this really does not work for all architectures that suffer from feature collapse. But this is very easy to implement because you can train like you do not need retraining. So you can take any pre-trained feature extractor and build a density model on top of it, and you're good to go. So in the next paper, like in our next paper, deep deterministic uncertainty, we kind of take cues from these previous works, and we introduce this like model called DDU. Before that, I wanted to show you this like toy experiment that we did. So let's have a ResNet 18, and the ResNet 18 obviously has a skip connection, and let's train the ResNet 18 with spectral normalization. All right, cool. And to compare that, we have to compare with ResNet 18 plus spectral normalization. We take a VGG16 and we take a Linnet, right? And we train it on this morphed synthetic dataset called dirty MNIST. What is dirty MNIST? So you have clean MNIST digits, right? And normally, for uncurated datasets, you could have a lot of noise, like things with aleatoric uncertainty in your data. However, normally for curated datasets, you do not have that. So to kind of simulate that condition, we make a dataset called ambiguous MNIST, which is basically we train a VAE on MNIST, and we take linear combinations of internal representations of the VAE and take the decoder of the VAE and get the reconstruction. It turns out that those images are kind of difficult to guess even from the perspective of a human, and that's why it's ambiguous. And of course, this can be done for other data sets as well. Now, the combination of MNIST and ambiguous MNIST forms dirty MNIST. And you could train your model on dirty MNIST, and you could have fashion MNIST, which is like a completely different data set of the same dimension as MNIST, but for like different products, like fashion products and stuff, as your out of distribution data set. So it turns out that if we take the softmax entropy of these models, then softmax entropy is completely fails. Like, so the in distribution in this case is dirty MNIST. All models have been trained fully on dirty MNIST, and they are being tested on both dirty MNIST and MNIST and fashion MNIST. Turns out that softmax entropy really confounds between these two. So for all three models, Linnet, VG16, ResNet 18, softmax entropy has a huge overlap between the two and is not really able to distinguish out of distribution. If we take the feature space density, then Linnet and VGC16 fail because they also like have quite high overlaps. However, if you take the ResNet 18 plus spectral normalization, that really works really well in terms like it actually gets more than 99.9 AUROC on these two data sets. So why does this happen? So in essence, what we are doing is we are learning, in very simple terms, we are learning good features which actually maintain certain amount, like a certain semblance of distance in the input space. And secondly, we are building this feature density model and quantifying our epistemic uncertainty on this feature density model. However, if you look at figure B here, then you can see that for MNIST and ambiguous MNIST, softmax entropy actually does a pretty good job of distinguishing between ambiguous samples and your actual MNIST samples. So softmax entropy does really well when it comes to ambiguous aleatoric uncertainty. However, it can lie anywhere when it comes to epistemic uncertainty, right? So what you want is you want to have two different heads, and you cannot really do it without having two different heads for two different kinds of uncertainties. So that brings us to DDU, which is you have a feature extractor with inductive biases, which is essentially to have a bi-Lipschitz. How you do your bi-Lipschitzness is up for research. We did it using spectral normalization and a feature extractor which has a skip connection, so to have that bi-Lipschitzness. And you take your epistemic uncertainty from the density model, and you take your aleatoric uncertainty from the softmax distribution. So essentially, it gives us a very simple algorithm. You could literally take, for any sample, you could first see the density, right? And that will tell you whether that sample is from a different distribution or not, because that quantifies epistemic, well, not uncertainty, because if you have density, then that's the opposite of uncertainty, or epistemic confidence. And if it has high density, which means it is lying in your training data distribution, then you look at softmax distribution. and the entropy of the softmax distribution. And that should give you your aleatoric uncertainty. So all in all, so that's how you have a single deterministic neural network that quantifies both epistemic and aleatoric uncertainty really well, actually. And how we saw this is we did experiments on active learning. And in active learning, what you have is you kind of want to train a model which performs as good as possible with minimal data, because you often do not have labeled data. So what you have is an expert labeling the data, and you introduce a certain bit of labeled data to the model, train it, and then see where its accuracy is at, and then you ask the model to, have a lot of some of the unlabeled data labeled by the oracle, say. So and in this experiment, you have the acquired data set size, and we run this experiment for both MNIST and dirty MNIST, where you have like in your pool set of unlabeled samples, you have either completely clean MNIST images, or you have a combination of MNIST and dirty MNIST. And to kind of crank things up a notch, in dirty MNIST, I think we used like 10% MNIST images and like the remaining all ambiguous MNIST. So when you do that, turns out that for clean MNIST, all the models really perform quite well. And the baselines here that we are comparing against is like softmax entropy. Then you have DDU. You have an ensemble. We tried an ensemble, and we tried both predictive entropy and mutual information. Like, remember, mutual information quantifies epistemic uncertainty, and predictive entropy quantifies both epistemic and aleatoric. So for the MNIST case, all the models perform really well. I think deep ensemble with mutual information performs probably the best, then DDU and so on. However, when we introduce dirty MNIST, then only the methods that capture epistemic uncertainty really well perform really well. However, because in case of MNIST, no matter what you are trying to get labeled, all of it is actually really informative data for your model to kind of absorb and retrain itself on. However, for dirty MNIST, you could end up in a situation where you have high softmax entropy for ambiguous samples, and you get ambiguous samples in, and that really does not help your training. You want clean samples, which will have high epistemic uncertainty but low aleatoric uncertainty in initial phases of training. So turns out that methods that actually capture epistemic uncertainty do really well when trained on a combination of clean and ambiguous data, which often happens in real life. So this was one of the experiments, and the other one was like a very, very classic OD detection large-scale experiment where we compared with, again, like softmax, energy-based, duck SNGP, of course, ensemble, and our method. And we found that, like, even on large-scale experiments, we found that our method actually has greater AUROC on SVHN. And when we take it with CFAR 10, when we take it with CFAR 100, the AUROC is far higher than 5 like for the ensemble. So it's like 87 compared to ensemble, which is 79. So that was kind of quite encouraging. So that, I think, yeah, the final one that I wanted to show is an experiment with semantic segmentation, and this is on a paper that is under submission, but we haven't released it on archive yet, but I wanted to show this result because it's really interesting. So the rows actually quantify, like they show. So first let me explain what semantic segmentation is. Semantic segmentation is where you are classifying each pixel instead of just an image. Like in case of image classification, you have a single image and you classify it to a certain class. In semantic segmentation, you classify each pixel to a certain class, right? So this was on the Pascal VOC semantic segmentation dataset, and the first column actually shows the accuracy map of these models, and the second column shows the softmax entropy. The third and fourth is MC dropout, predictive entropy, and mutual information. The fourth and fifth is ensembles, predictive entropy, and mutual information, and the last one is DDU. DDU feature density, that's what I mean. Because DDU is a combination of both the second column and the last column. So it turns out that if, like, entropy, as I mentioned before, captures aleatoric uncertainty, and it's really high on edges of objects, because that's where the transitions between different classes takes place. And as we saw before in our toy experiment, that's where also aleatoric uncertainty is high. Whereas in case of epistemic uncertainty, it's actually high in objects where the network is kind of misclassifying a lot or which is out of distribution. For instance, what was particularly interesting to me was this like last row where we have like a huge couch, which is sort of out of distribution for the model. And DDU kind of captures just that. And it's not really that focused on the edges. So combination of that really works well. And the catch, like the best thing is that if you look at the runtime over, like we did it over like averaging over 10 single forward passes, and for different so we did this experiment averaged over 10 different models, and for the dropout method, we had 5 stochastic forward passes. Turns out that for five stochastic forward passes, it takes around 1.5 seconds to just pass through like one single sample. Whereas DDU and softmax, both being completely deterministic, are almost around the same, 263 milliseconds and 275 milliseconds. Whereas deep ensemble is also much higher. It can be done parallelly, but it takes a lot of memory. So deep ensemble is more memory intensive than temporal, right? So that's kind of the takeaway from here, that you can actually get very simple ways of computing or quantifying your uncertainty estimates by making minimal changes to your model, and that really helps in large scale applications where you are actually constrained to make real-time predictions. And if you can quantify the two different kinds of uncertainty, then that really helps for both out of distribution data and in distribution noisy data. So it also helps in case of getting different responses from your model, and it also helps kind of explaining what kind of uncertainty or what kind of data is being sent to the model, because noisy data is because of certain reasons, whereas out of distribution data is something else. I think that's about it. And yeah, we have Happy Raccoon there. Those are the references. Sorry, I think I introduced those slides twice, but that's about it. And please feel free to ask me as many questions as you want. I think that's about it.
Yes. Thank you, Jishnu, for this wonderful lecture. And keep your screen shared. So I have a couple of questions in the chat box. So maybe it will be helpful for you to.
Of course. Okay. Is the screen shared?
So we have a question from Shreya. Can you please explain the difference between ensemble versus single model architecture in DL?
Right. So in like a single model architecture, you just have for instance, you take a ResNet and you train it, and that's your single model. An ensemble is just multiple models. So you have, say, 5 different ResNets, and you have a training set, so CFA10, and you're training 5 different ResNets, and then you're averaging the prediction. So let me go back and show it to this slide. Yeah. So in case of an ensemble architecture, each of this is just a plain vanilla simple neural network, right? And then in your ensemble, you get a softmax distribution from each vanilla plain neural network. And then what you do is you average the softmax distribution, and then you can compute uncertainty of that averaged out softmax distribution as your equivalent. Or you can do like other things. Was that did I able to answer your question?
Okay, so I have another question from, I don't know his name. So it is AB asks that in case we apply data augmentation, so it is related to data augmentation. So Jishnu, can you please show your screen, because otherwise it will be cascading for screens. Keep your slide on. Yes, somewhere. So I hope you can read the question.
I can't read the question actually, like if I'm on a different tab.
Okay, so the question is, in case we apply data augmentation, will it affect model performance in terms of uncertainty?
So in terms of uncertainty, your model kind of gets better. So if say it depends on what kind of data augmentation you're applying. By applying data augmentation, you're kind of what you're doing is you're putting in more, possibly more noisy samples from your training distribution. However, the model does not really get better in terms of out of distribution because your out of distribution set. I know there are a lot of papers which say that training on augmented data helps uncertainty, but since your out of distribution set is completely infinite, you cannot really have any simulated out of distribution set. If you have a simulated out of distribution set, then your model will perform really well on that simulated out of distribution set. However, your out of like you can still get something that you have never seen before, and there the model will fail. Also, this brings me to something called OD, like outlier exposure. So you can train with outlier exposure, but that also suffers from the same problem because you can have an outlier that you have never seen before, which is outside your outlier set.
Okay, so one more question, I'm just posting it. This is from Ayush. So Ayush is asking, like, is the rapid decrease in loss after around 150 pokes an experimental observation or some theory, or some whether there is any theory behind it?
Yeah, so this is a good question. So sorry for I forgot to mention we have learning rate drops at epoch 150 and 250, and that's what's causing this drop. So every time that you have a learning rate, so we train with like like point 0.1, starting with point 0.1 from 0 to 150, and then 150 to 250 was 0.01, and like drop by a factor of 10, and that caused the loss to decrease because if at a certain after a certain level, like it cannot decrease further without using a learning rate drop. Of course, you can have other learning rate schedules, but you will have pretty much the same observation with all learning rate schedules. But these significant drops are is because of this learning rate schedule.
Okay, so very good. So if you have any other questions, you can actually drop in the chat box quickly. So till that time, like I have just one general, I was curious, like you explained very nicely. So uh, are there any real life applications that you are working on, like in your lab and all? So can you I can see that you experimented on MNIST, RDMNIST and all. So any real life applications are you planning?
So the thing is that we in this like BDU paper we did on MNIST, dirty MNIST, and then CFA10, SVHN, and stuff like that. But the real life application that I'm currently working on, which was basically the last slide, was semantic segmentation, which is kind of used a lot in autonomous driving, and
Okay.
also I'm currently also looking at other architectures, although that would not be like a real life application. But yeah, I would say the biggest application that I'm working on and applying this uncertainties to would be semantic segmentation.
Okay. Thank you very much. So,
Okay,
any more
I have one or two
questions?
questions. Can I ask?
Of
Yes.
course.
Maybe very simple questions, or may not directly go with the track. In one slide, probably you said that like you are adding a distance hour layer, and you have said that you can put some restriction on the feature extraction. So my question is like, people really try that? Like, can we
Yeah.
put some restriction in the feature extraction? So otherwise, like deep learning model, if we add some constraint, so will there be any auto learn thing?
So by restriction on the feature extractor, what I meant was for like to have bi-Lipschitzness. That's what I meant by restricted feature extractor. So what I want from the feature extractor is to have a semblance of distance in the input space. And normal feature extractors that are like, available these days off the shelf fail at that. So people actually are trying out different kinds of ways of kind of having bi-Lipschitz feature extractors. In fact, PyTorch, I think, recently released a complete like spectral normalization layer because it's being used so much. Like you have a pre-made layer. But I'm not sure about AutoLearn because I'm not very well aware of the AutoLearn literature. But this feature extractor, by constraints, I just meant by Lipschitz. And you do not have to do anything other than just spectral normalization. Also, one other actually, yeah. So this kind of brings me to one other point, which is if you have sensitive features, they're often enough. So if you have features which are sensitive to inputs, distances in the input space, where you are introducing sensitivity because not of spectral normalization, but because of the residual connections, which is lower bounding your Lipschitz, right? So if you have sensitivity, that is often enough. So we did an ablation where we removed the spectral normalization, and we found a performance drop, of course, but that performance drop is not that significant. However, if we remove the residual connections, like if we try with an architecture which does not have the residual connections, that has a massive performance drop because it does not work. That's why I said that Mahadana this does not work because it really like as you can see for BGC16, it confounds with OD and in distribution data. So that's what I meant by constraining the feature extractor.
I was thinking maybe if we do that, I mean, if some researchers they're doing this, so we can lose some sort of generalizability of the network. Maybe we can put some restriction for some data set, but that may not work for other data set also. So that was I'm thinking.
Okay, I see. So when you're like, this is a restriction that you're putting for any like training distribution that you have. It is not data set dependent.
Okay. So another question was you are talking about dropout. Maybe you have used a term also, variational inference or something like that.
Yeah.
So my question is like people use dropout randomly, some percentage. So can you explain something like is it really useful if we do some random dropout?
So
So what's your thought on that? That's my question.
Sorry.
If we do some random dropouts, then will it be useful? So that is my question. What do you think?
So if you have, when you're training your network with dropout, you normally set a dropout rate, and that is a hyperparameter, right? So when you're actually doing variational inference, that dropout rate actually becomes a variational parameter. So ideally, what you should be doing when you're using dropout, MC dropout, is kind of fine-tune that dropout rate. Like you can do, if you're kind of like trying to brute force it, then you can do a simple grid search over different dropout rates, but that becomes very computation again, like very computationally expensive, like because you have to train so many models. You can also try doing concrete dropout. There is another paper called concrete dropout, which actually fine tunes the dropout rate during training itself, but it involves like more architectural change than a dropout. However, if you so like I think dropout rates are kind of a bit heuristic because normally you have
Yes.
certain dropout layers after certain layers of your network. You do not have dropout after every layer like this paper actually proposes to do because this wants a dropout after every layer that you want to create a distribution on that you then generally do not do. However, you can still work with dropout layers which are there after only certain layers. However, you have to very carefully fine tune your dropout rate for it to work properly. And like uh, that takes a lot of compute. So random dropouts might work like in the sense that they will regularize your network. But if you want to do random dropout during test time, then and for the purpose of uncertainty, then you have to fine tune your dropout rate for it to work properly.
Okay, so there is another question from audience.
Yeah. Oops.
So the question is how uncertainty apply in unsupervised learning.
Ooh, that's a very good question. Unsupervised learning. So I think in case of unsupervised learning, you have uh, you have generative models, and there was this whole bunch of literature which tried generative models on to capture uncertainty. Because what your generative model does is it captures p of x. Normally in discriminative models, which is all what I talked about here, you have p of y given x, right? What if you model p of x? And if you model p of x, then ideally for something that has low p of x, that should be ideally out of distribution. And people wanted to work with that. However, empirically, it turned out that I think p of x for out of distribution data turned out to be higher than in distribution data, which was a very weird empirical observation. And I'm not sure very well explained yet. But so people kind of thought that, oh, well, generative models do not really get what we're thinking in terms of uncertainty. But that's a very good question. And in terms of other unsupervised learning, I'm not very sure. Like the only thing that I know about unsupervised learning and generative modeling is this: like that people have tried this in the past to get uncertainty. I'm not sure that worked.
Okay, so any other questions? Anyone in our panel?
I can also share that paper. That's a very good question, actually. Unsupervised uncertainty.
Okay, I don't
Okay.
know your idea. You have said simple, fast, and practical. So I don't know how much simple it is, but it may be fast and practical because we generally use ensemble technique, and we thought like that uncertainty can be captured using the ensemble model. That is the common thinking. But we did not. At least my team, we did not think, never think like this way. So maybe this is useful for our team and others who are listening here.
I mean, so if you're working with like a very practical suggestion, if you're working with networks like content networks like ResNets and wide ResNets and dense nets and so on, uh, even if you do not train on spectrum normalization, even then you can actually get pretty good uncertainty by take a trained model, and then just say for each class you compute the mean of the features, and then you compute like a covariance matrix over features, and just doing that, so you can, like, PyTorch has predefined methods for all of this. Like you can create a Gaussian mixture model, which can be your density model, and you can just take like the log graph from that Gaussian mixture model as your uncertainty. So this is quite simple to implement. And oh, I could also share code. So sorry, I have not actually linked the code links for my work. Both of them are available, and you can have a look. Like I can share this. I don't know how I will share it. Maybe.
Okay, and someone is asking your email ID also. So if you want, you can share
Yes,
that.
yes. So this was very recently released. This has the code link for DBU. Can I share it on chat or something?
You send it to
If you share,
me. I can actually share that. Just a minute.
So let me just move to another slide. Code.
Your Gmail ID. Should I share your Gmail ID?
Yeah. My Gmail ID is jishnumukhoti7@gmail.com.
Okay, I'm
And
just sharing that in the chat box.
yeah, so both the code is available. So please go and feel free to have a look.
If you Do you see any chat link or something? Then you can send me a private chat or something. I can post it here.
Okay, I'm
Or
going
if
to switch to
you,
this tab, which will cascade. I'm sorry. But so this is the code for DBU. Also, I can stop sharing if people don't have any more questions. Code for DBU is for validation. Uh,
Okay. So will it be available for us or the audience also, Professor Basu? The links?
I'm sharing it. Just a minute.
Yeah,
Okay.
it will be for us, I guess.
The code for DDU.
I sent it to private chat.
And he shared his email ID also. So he just
So is it okay, Jishnu, if I share it with the whole team or?
Yeah, of course, please do. Like, and
Okay.
also please feel free to ask me further questions over email. Please drop me an email. I'll try to answer them as best as I can.
Probably you
Okay,
can
I'm just
share your
sharing.
Google Scholar profile or so, link for
Uh,
the profile so that they can search for it.
I think that is the best way. If someone is interested, they can find this here. And with this, we are actually, if we do not have any further questions, I do not see any questions. I, I think one more question is there. Just a minute.
can
Vishnu,
comparison
can you
of
see this question? Yes.
test uncertainty and train uncertainty using loss value can be potentially a useful metric for performance evaluation. So, so on your training set, you are supposed to be first of all like we have to define what test uncertainty and train uncertainty you mean. I am assuming that you are saying, say, softmax entropy on the training samples as your train uncertainty, and the same thing for test samples as your test uncertainty. In that case, after training, you will always end up with a train uncertainty which is very, very low because the model will have very peaky distributions, like almost a delta distribution on all your test train samples, which is why, like in the calibration, like the plots, it was like the entropy of the softmax distribution kind of completely flattened out at almost zero for train sets, training samples. However, your test uncertainty can be high, of course, but comparing them using a loss value, again, like it depends on what performance you're evaluating, but like whether you're evaluating generalization or whether you're evaluating like uncertainty quantification. I think like I don't think so. I don't think that train uncertainty will really be helpful because train uncertainty after training will be really, really low for all samples, for all training samples. Like not off the top of my head. I can't think of a reason.
Okay, so Rishabh, I think it's more or less answers your question. So if we do not have any further questions, so I must take this opportunity to thank Jishnu, and I just want to share my screen and just wanted to say thank you. So
Thank Thank you.
just token certificate of appreciation from
So can we
the
clap?
computer chapter of technical only within the small group. So let us be a bit informal now. So we were actually thinking about having some informal discussion with you. So we were in a bit dilemma whether we should have the discussion before the presentation or after the presentation. So we thought that maybe since this is more of a specified technical talk, so we should rather take it at the last and give higher priority to the presentation. So we always wanted to hear from you on your journey and being an you know being kind of a we want to see like as a uh, budding technocrat, that term that we are using, and as a role model maybe. So maybe for the young aspiring engineers. So maybe if I request Professor Sharkar and if Dr. Chaudhary, if you can have a informal chat with Jishnu on his journey, and if you can share something to the student community. Over
Okay,
to
actually,
Professor Sharkar.
uh, Vishnu, we used to work on 2015-16, I guess, in that year, in your final year. So during that time, I knew that you wanted to do higher studies. You sometimes used to say, even after that also, we used to talk via phone or even other medium also. So I knew that you wanted to go some like big university. So my question is like, if you share few words, maybe the current students, the juniors, they will get motivated. They will also think of something big. So I think after 2016 you joined industry,
Yes.
and then you came back again for your higher study. Okay, so I think it is better you share your journey.
Yes, of course.
How did
Uh,
it started?
so
And
I
which motivated you? What was your motivation to switch from from industry to academics? So maybe the people who are listening, most of them are aspiring to be a successful engineer in an established industry, but you chose a different path. You were always good. You could also do good, very good in industry also, but you chose a different path. So what motivated you? That is I think it's better to listen from you. Please, I interrupted.
No, of course not. I after finishing my time at JU, what I basically during even during my like course during JU, I quite loved research, and I have worked with Professor Ram Sarkar, and actually I even did a project interview Shodi sir. That was kind of like part of coursework, but I remember having done like an Android project and stuff. Um, so I really just like I loved research, and just reading papers, looking at like because research is kind of like absolutely at the edge um, of knowledge. So I really loved doing that, and the passion of the professors really also was very very inspiring. And I also worked with Professor Amit Konar. He's in the electronics department. So both my mentors were so very, very great in actually helping me learn. Um, like I think I don't know about students right now, but I took a lot of time to learn about how to write a research paper. I was really bad at it, and both my professors really, really helped in that regard, and their passion and it was amazing. So yeah, I really love research, and then I went to the industry because primarily because I received an offer. So I went for an internship in Amazon as an SDE after my third year. And that was like a 3 month internship. And then I got the offer. And so I went for a year because primarily because I didn't think that my application to higher studies would have been very successful in like top schools. So I went to the industry for a year, and I was there in Amazon as an SDB. And during my stay at Amazon, I was looking into like different ways of kind of going into higher studies. So that's when I applied for the like during my stay at Amazon, I applied for the masters in computer science here in Oxford. So um, even there, my mentors really like Professor Sarkar and both Professor Konar as well and Professor Shudip Naskar. They were basically my three LORs actually, and that was really very helpful. So after that, I left Amazon because I wanted to do further studies and I wanted to eventually get a PhD. So that's why I came to Oxford, and here I met during my masters. I actually met Professor Yaron Gal, and I worked with him for my master's thesis, which was actually on semantic segmentation, which I talked about. And so that's how I like. So it's very important, I think, to make contacts, and especially to be fair, like getting a PhD offer in Oxford is quite competitive. So I think having contacts really helps. So, so yeah, and after working with Professor Yaren here, I got in touch with Professor Philip Tor and wanted to do an internship here. And so I did an internship, like a completely research internship, and then started my PhD. So I'm in my second year of my PhD, and I'm co-supervised by both of these professors. And yeah, I would say my driving force would be kind of, I just love these.
So
Yes.
you can still
I'm
join
very pleased with
industry
it.
after finishing PhD.
Sorry?
You can still join industry after finishing PhD or academics. The choice is yours once again.
Yes. So I would like to be in whether academia or industry. I would like to be in a place which does open research, like open research, open source code. Everything I really like that, and open reproducible research. I really like that, and so I think there are a lot of places in industry which does that as well, which is really good for me, I guess. But but yeah, academia, of course, like gives you, I think, a higher amount of freedom. I haven't yet decided which where I would stay, but whether industry or academia, I would want open research.
Since there are many contents that are available open, as you have pointed it out, open source, and maybe there are some blogs as well which really discusses the topics well, but sometimes since these are not well reviewed, so we are very much confused whether to follow that or whether to suggest it to the students or not. So what do you have any suggestion in that, particularly
So
for this machine learning part? Yeah.
I completely understand, and I know that putting your paper out, especially on archive, and it has its own weird dynamic because you have conferences which you put your paper on archive and stuff like that. I think because the field, especially in, and I'm speaking about particularly about machine learning, and because the field is moving so very fast, I think it has kind of become like a part of the game to kind of popularize your work by putting it on archive and then advertising it and putting the code up. Of course, I think that any work that is going on archive should, like, even if not immediately, should have eventually have the code because yeah, like reproducibility, especially in a field where there's such a rush of papers coming in, reproducibility
Yeah.
is very, very important. And so code is very essential. But I'm like I have two minds about putting papers. So the first paper that like actually got into NeurIPS, that was on focal loss, we actually held off putting that paper on archive for quite a bit. And then like after I think two conferences when we submitted the two conferences and got rejected, and the third conference that was when we put the paper up on archive. And I mean it's up to you really, but it really plays unfortunate but true. It really plays a part in how popular your paper gets, like advertising and putting on archive and advertising code and then writing a blog. I think writing a blog also really helps, and then advertising the blog. It's it's just an unfortunate part of the game, I feel, especially in machine learning, just because it's so fast.
Yeah, it's true. So I think we have.
Professor Basu, please
Should
unmute yourself.
yeah, you are not audible. Yeah.
Okay, sorry.
Okay,
So I
so
was just asking, like, what would be your suggestions for the mm, for our maybe final year students and all, so who are aspiring, so
I mean, to be fair, like,
graduating.
just do whatever. Like, you are graduating out of JU, which is a really, really good school, and just do whatever you like. I again know that this is very cliche, but just do what really you like. Like, if you want to become an engineer, and if you want to go, like, there is a lot of scope for growth there as well. And then, like, if research really drives you, then you can apply for. And also, one thing is that a PhD is kind of a marathon. And I'm speaking from a school that has a 3 to 4 year PhD, whereas in the US it's like 5 to 6 years, a much longer marathon. Um, so, I feel that unless you really love what you're doing, think before you jump into a PhD. I know a PhD has like a an aura about it, I guess, or some people really like, oh, just having a PhD, but don't do a PhD just, well, that's my opinion again, but you know, it's it, it's a very, you have to make a very consistent effort throughout the course of your PhD to kind of get there, and there are many other ways. So do what you love, and yeah, I mean, that's pretty much it. Like, just do what you find is good for you.
Okay, so anything else, Professor Sarkar?
no, I think now actually this is 8:41, so you can
Yeah,
now
just
end
one
Okay,
it.
last question I have. Like during this pandemic period, when everything is online, particularly in India, the situation is not at all improving. So, like for a sustained period of time, I mean, we have to switch to online teaching, online learning, everything. So there the things are really, I mean, sometimes it becomes very difficult for students to cope up due to many different problems and internet connection and all those things. So how you are doing at your end, or during your, I mean, pandemic period, how things are adopted? I mean, can you give any suggestion from your part, the way it is handled at your university, the way you have seen? Do you
Yeah.
have any suggestion for us?
Well, I mean, I can say what happened here. It was, I completely understand the fact that students are having a difficult time to cope, and even I think professors, like even professors here, um, did face difficulties during the lockdown. And myself, as like, I actually stayed here. I have not been home for around, I think, like slightly more than 2 years now, and almost going to be 3 years this September. Actually, much more than 2 years. So, so yeah, like, it's very, very difficult. Just the only thing is that uh, just hang in there. But I think in Oxford, what happened was that the good thing that the university did was that they called all the students. So the students are actually here. Like, a lot of the students actually came here, although the classes were online. So they were here in the city, although the classes were held online. And now that UK is starting out of lockdown, I think slowly they will start having interactive, like, classes as well. Like, I don't see that situation happening in India anytime soon, uh, because of, yeah, it's really it's not that good. But I mean, my suggestion would be pretty much to, like, when vaccination, like when the numbers drop, having a combination of online and offline classes, maybe that will help. And I mean, there's really no other way to be fair, but it all depends on when things get safe for people. Um, and yeah, I mean, just for the students especially, and even for professors, I think like uh, take care of yourself because it's really a difficult. Like at least I had a very difficult time during lockdown sometimes. So yeah, I can totally imagine it's not that easy.
Okay, so Chandra, any further questions? It's already 1 hour 45 minutes, so I
Yes,
can
yes.
feel
Okay.
that Jishnu is continuously speaking for close to 2 hours now, and I think it is high time that we put an end to the session. And as the computer chair, computer society chair, like the chair of the computer chapter of IEEE Kolkata section, I take the responsibility to for the vote of thanks and to make this webinar like the webinar series on listening from the budding technocrats. So I must first thank Jishnu for accepting our invitation to be the first speaker in this webinar series, and we are planning many such lectures from young budding technocrats. Like these days there is a term like digital fatigue, and either you are giving lecture or listening a lot of lectures from very senior people, and sometimes fatigue is there, so we wanted to organize it in a bit different way from the youngsters like you. And thank you very much, Jishnu, for giving such a wonderful talk. And we would like to be in touch with you for many such programs in the future.
Of course,
Okay, thank you.
I love that as well. Thank you.
And I must thank the executive committee of the computer chapter, the whole team. They worked tirelessly, and it is not easy for us sometimes to organize an event, especially during the pandemic period. And it would not have been possible, to be honest, it would not have been possible absolutely without the help of a very efficient team we have from the uh, student branch chapter, CS student branch chapter, like the very good team led by Prithijit, who is the CS chairperson, then Mayank Agarwal, secretary, Bipornok, the technical head, Shreya, the secretary, and Tamodip, the vice chair. So I must thank all of you, and not just them. So we got a very good participation. Even when the talk was going on, they were Bipornok was posting links, some technical problems here and there, and we are slowly, as Jishnu, you can also understand, we are also, edging out. So technology aspect is also, technology is moving a bit faster. At There were times like we used to call ourselves like we were the savviest people. Now it's not. I must admit that without
Exactly,
Prithijit's
we are not.
suggestion, I didn't know about this. What is this platform called? Like StreamYard. Okay, so I was thinking about Google Meet. So Google Meet, Zoom, Team. So we tried, but we could not connect to YouTube Live. So that was a problem. So Prithijit and their team, they helped us, and then we could actually manage it. And it's really good. And I think we can arrange more meetings in using this particular platform, StreamYard. And overall, it is a very good team, very good coordination from full IEEE team, from our executive committee as well as the student branch committee, not just from JU, and also we have student branches in other institutes like IEM, Netaji Subhash, and also in Meghnad Shaha Institute of Technology. And I also take this opportunity as the chair, and it is my responsibility to also promote IEEE. And I must request all those who are listening to this and will be listening to this recorded version of this live, that please join IEEE as a student member if you are a student, or as a mm, full member if you graduate. If you join industry, you can also become a young professional. We have a very active young professional chapter in IEEE. And as far as the student branch activities are concerned, students are really doing wonderful. I also right now we are planning about some hackathons, and also students are always trying to organize so many things, and this is an excellent platform to not just network, socialize, also to showcase your leadership abilities and to learn new things. Like we are also learning new things, and learning never ends. So I think IEEE gave us this wonderful platform to all of us. And last but not the least, I must thank IEEE for this wonderful, providing all of us this wonderful networking opportunity. Thank you very much. And finally, thanking Jishnu again and all our in the panel, Professor Sharkar and Chandri. Thank you again, and all the listeners who are there. So with this, thank you very much.
Thank you,
Thank
everybody.
you. Thank you so much.
Thank you. So I'm closing the broadcast now. Those who have participated and filled up the form, so they will get the participation certificate in due time. Okay. Thank you very much. Thank you.